We'll get started. So we've been discussing about approximate dynamic programming. It's a very important area, both from a research point of view as well as applications point of view. We've learned so far about how to solve dynamic programming, how to solve dynamic optimization problem. There are two different methods. One is maximum principle or minimum principle, depending on which book you read. Attributed to Pontryagin, developed back in 1948. And the second one was dynamic programming, attributed to Bellman, but was actually discovered by Isaac before Bellman back in 1949 to 1952. We learned that solving optimization using Pontryagin minimum principle is extremely easy because it's just gradient descent, and the co-state vectors are Lagrange multipliers. So in some sense, you can design an easy algorithm called backpropagation algorithm in order to solve that gradient descent problem, and you can get an optimal solution. But the optimal solution is open loop. What that means is, in case the state gets perturbed at some point of time in the future, you have to recompute the entire optimal solution all over again. And that's bad. So how do we fix that? We fix that using dynamic programming, where at every point of time, you compute a value function, you compute a policy, and you keep going backwards, starting from the terminal time step. But the problem there is, if you have a very complicated, high dimensional, high long horizon optimization problem, like we are going to Mars, or we are going to Jupiter, or we are going to, I don't know, home, and I need to make a decision every 100 milliseconds, then it becomes a very complicated problem to solve. Especially because I have to solve the problem globally. So I have to at every point of time for every state that I'm potentially going to visit, I have to solve that entire dynamic programming problem. Then we said, okay, there are multiple approximations that we can do. If you have a long time horizon problem, then we can use model predictive control, and we can use rollout algorithm in order to solve that problem. And so the MPC and rollout were two algorithms we discussed in the previous class. Today we are going to talk about what happens if your cost function is complicated and your state transition function is complicated. So that's called a model approximation and cost approximation. So that's what we are going to study today. In the subsequent class, we are going to talk about, now I have these two functions that I have to keep track of at every point of time. I have a value function to keep track of, I have a policy to keep track of. And again, that's very complicated. So far, what we have said in the class is I'll create this very long rule book. And in that rule book, for every state, I'll note down what the value function is, and I'll note down what the policy is, what the action should be. And as you can imagine, in an uncountable state space setting where we have Rn as our state space and Rm as our action space, this rule book is going to look infinitely long. And how do I compress that infinitely long rule book into something that I can store on a computer and look up at every point of time? So we'll talk about that in the subsequent classes. So today, our goal is to do model and cost approximation. I'm not sure whether I'll be able to finish the two topics today or not, but if we are able to, that's great. If not, then I'll again we'll study the rest of the topics on Monday's class. Okay. So I have the problem xt plus 1 equals to ft xt ut. T goes from 0 to capital T. I have my cost function j. We are using pi as our policy, right? So I need to compute pi. I need to minimize over all pi. Ct plus 1 xt plus 1 plus summation t equals 0 to capital T ct xt ut. And for the purpose of first part of the lecture, I'm going to assume that there are no constraints. We did have constraints in the previous classes, but right now, for the time being, let's just assume that there are no constraints, because the constraint case is a bit more complicated. We'll probably talk about, we probably will not talk about it, but if in case we need to, we'll talk about it later. Okay, so this is the problem statement that I need to solve. All of this is reasonable. T is reasonable. Everything is reasonable. The only problem that I have is I have a rocket. It has multiple degrees of freedom. It has a very complicated dynamic. So this Ft looks awfully bad. The cost function is very complicated as a function of the state and action. So there is this rocket has a fuel, rocket has a mass, a lot of things are changing, the fuel is burning, mass is changing. So it's a very complicated cost function over time. And I need to send this rocket to space and launch a satellite in space. So this capital T is maybe like 10 minutes long duration thing that I need to solve. Okay, so this is the problem statement. My Ft is very complicated, my Ct is very complicated. How would you go about solving this problem? Any thoughts? What would you do? So yeah.
The neural network to approximate the transfer function.
We are not at the neural network yet. We will go there in the next class. But no, we are not going to approximate the cost function right now with a neural network. You have a complicated function, you have to use a complicated neural network to approximate the function. So you're not really reducing the complications of the problem. Any other thoughts? What would you do? So I'm going to push you back to 1965. We have to launch Apollo mission in two years. We have to send man on the moon in 4 years. And we need to send the rocket to the moon. And this is the problem statement that needs to be solved. And my rocket is complicated, my satellite is complicated, people are complicated, design is complicated, engineering is complicated, everything is complicated. I want to simplify my life. Okay. Any thoughts?
I'm approximated as so is that the coordinate function of
Sorry?
Maybe we can approximate use some type of surrogates and then such that it will be convex in terms of our decision variables.
Yeah, okay. So you want to use some sort of surrogate. So you want to maybe come up with an upper bound or a lower bound on the cost function, which is maybe convex or something like that. So solving that becomes easier. Certainly you can do that. But if you come up with a surrogate for the cost function and a surrogate for Ft, I'm not quite sure what I'm computing at the end of the day. If I add so much approximation that I don't even know what I'm computing, then what's the point of computing that? The answer is much simpler than that, by the way. You guys are coming up with very complicated things don't move the frontier. The easier things actually move the frontier. So what's the easier thing that you can try? I'm going to remind you of the movie Hidden Figures. If you have not seen it, go back and see it. If you have seen it, refer to it in your brain and try to tell me what exactly would we do in this particular situation. You have a thought? Yeah.
Is Euler's method involved?
Euler method is involved in computing this Ft. That's where the complication comes from. But now somebody has told me like this is what the Ft looks like, but it's complicated. There is some 10-dimensional state space, 5-dimensional action space. It's just very bad.
Augmenting the decision variable space, we are only considering U terms. We can also consider X terms.
We can, but I see the thing is that the problem is very simple as soon as you get to the heart of the problem. So I have this rocket that I'm supposed to send to the space. The initial point of the rocket is fixed. The final point of the rocket is fixed. Some scientist gave me the trajectory that I'm supposed to follow. And this is the problem statement that I need to solve. What would you do? Yeah.
Maybe change the definition of the state and the transfer function.
Yeah, okay, so you want to change the definition of the state and probably change the definition of the action, right? So if I change the definition of the state and action, how would that help us? There's just 2 words, and we have been using those 2 words throughout the semester. So I just want somebody to tell me what those 2 words are.
Nonlinear?
Yes, nonlinear. Ft is nonlinear, Ct is nonlinear, but what do we do?
Transition is nonlinear, and then we have that some type of trajectory.
Yes.
Linear at every point.
What is the term for that? How do you linearize a nonlinear function?
Taylor?
Yes, Taylor series. That's the word I was looking for. Okay. So somebody gave me x bar t and u bar t, t equals 1 to capital T. So somebody told me what is the trajectory of the system supposed to be, and what are the actions that have, at every point of time. If everything was perfect, x bar t would be the trajectory, u bar t would be the action that I'll be taking at every point of time. How do you compute x bar t and u bar t? You go and talk to people in physics department, astronomy department, whatever, all these people all over the place. They will tell you that this is what the ideal state should be and this is what the ideal control action should be. You are trying to solve a battery pack problem, you want to optimize the battery pack for something. The material science people who are building that battery will tell you what the ideal state should be and what the ideal action should be. Do not charge too much, charge it at this temperature. If your temperature is high, then you have to put this much current in the battery. This is the internal resistance, this and that. That is all the stuff that material science people do all day long who are designing batteries. So they will tell you what x bar t and u bar t should be. What happens in real world? Perturbations. There is wind blowing, there is temperature changing, I'm driving the car like there is no tomorrow, and my battery pack is heating up like crazy. And so I'm basically adding perturbations into the system. And the good thing with perturbations is always small in comparison to the state. So the approach that we are going to take in today's world is we are going to assume that the perturbations are small. If I'm sending the rocket to space, I can assume if the rocket is flying at 10 kilometers per second or 5 kilometers per second, the perturbation could only be of the matter of 100 meters per second or something like that. It cannot be like I want to drive at 5 kilometers per second and suddenly the velocity becomes 20 kilometers per. I mean, that's just not going to happen. So it's always going to be small perturbations. And all I have to do is compute the feedback law, like x bar t is where I should be at time t, but xt is where I am at time t. Xt is not too far from x bar t. U bar t is what I should be applying to the system, but ut is what I am actually going to apply because there is some perturbation to x bar t. So I'm going to figure out what the right action I need to take from this ideal action, which is u bar t. So what's the right perturbation in the action I need to make in order to optimize this particular cost function? Okay, so the idea of this particular thing dates back to 1950s and 60s. And what we are going to do is use Taylor series expansion and solve this problem. Okay, so what's my current state? So my true state xt is x bar t plus, I'm going to use delta xt. I'm using it for historical reasons. So in historical papers, people use delta x as the perturbation to the state. So I'm using that notation here. And then my ut is going to be my u bar t plus delta ut. Okay, so some people use delta xt, delta ut, some people use this small delta. I'm just using small delta, but if you're reading some old book or old paper, then you might have slightly different notations for this. And as is the case, x bar t is the majority of the state, and this one is just a small perturbations to the state. Yeah.
So we are not solving the global solution.
We are not solving the global. I know exactly this is the Earth, this is the moon, this is the path that this thing is supposed to take, this rocket is supposed to take, and I'm only going to be slightly away from the path at every point of time. And I want to reach the specific point in the moon. And it's okay if I'm within 100 meters of that specific point. It's not like I want to go to North Pole and I end up reaching South Pole. That's not acceptable. But if I'm trying to reach the North Pole and I'm like within 100 meters of that North Pole, I'm happy. I'm not going to complain about it. Okay. So this is going to be small perturbation. I mean, you can apply this thing in any chemical factory, whatever. If you are running 500 megawatt generator and somebody turned on their iron because they wanted to iron the clothes, now the generator has to generate all that electricity in order to for you to be able to iron your clothes at home. Okay, so that's delta. That's the small perturbation that you're making to the state or the action of the system. Wonderful. So whenever I see this delta term here, whenever I see something small, then the light bulb of Taylor series turns on in my head, And now I can do Taylor series expansion of all this stuff. Wonderful. So I have x bar t plus 1 plus delta x bar, sorry, delta xt plus 1 xt plus 1 equals to ft x bar t plus delta xt u bar t plus delta ut. Can someone do the Taylor series expansion of this function and tell me what I get, what I should get? I need your help. Wonderful. Okay. This is a matrix which is in Rn cross n. Okay, so xt is in Rn and ut is in Rm. This thing is in Rn cross m. This thing is in Rm plus higher order terms. Okay. I have the second order Taylor series, third order Taylor series, fourth order, fifth order, sixth order. I'm going to ignore it. Because my delta is small in comparison to f, so delta xt square is not going to make a big difference, or delta xt, delta ut terms are not going to make a big difference. Those are small terms. Okay, wonderful. I have ct plus 1. And this one, by the way, this one is my x bar t plus 1. Any questions on this? Sounds reasonable? Okay, we have done Taylor series so many times in our life so far in this class that you will never forget until you die about Taylor series, right? Now we'll do the same thing for CT of xt, sorry, x bar t plus delta xt, comma, u bar t plus delta ut. This is CT of x bar t u bar t plus I'm now going to use the short form notation.
Short term, we forget instead of current, we put data. Yes.
Oh, I'm so, yeah, sorry, this is derivative. I'm so sorry. Thank you. Thank you. Yeah.
Do we not have cross terms?
There will be a cross term also, the second order term, but I'm going to ignore it. I'm going to put it in the higher order terms. And the reason for that will become clear in a bit. Yes.
Why are we using the first order on the transfer function, but the second order on the cost?
Very good question. Why are we using the first order term in the state transition function and second order term in the cost function? Uh, Assignment 6, problem 1. Have you started your assignment yet? No? Okay, that's where the answer lies. Okay, I'll tell you why we are doing it in a bit, but the assignment will make it more clear. Any questions so far? Any other question? Okay.
Maybe we have the a priori information that it will be quadratic.
Not quite. It has nothing to do with.
Post-definite product.
No, I don't think. I don't think it has something to do with. Let me get to it in a bit. Okay, I'll get in a bit. It's a very important technical problem. Okay, and I'll talk about it in a bit. Okay, so I have done the approximation for the state transition function. I've done the approximation for the cost function. The only thing I really care about is delta xt and delta ut terms. I don't care about. So let's for the time being ignore the higher order terms. Okay, here. And because x bar t plus 1 and x bar t plus 1 appears on both sides, I can sort of cancel it. So what I get is delta xt plus 1. I'm going to call it at. I'm going to call it bt. I'm going to call it qt. And I'm going to call it rt. These are all matrices. These are all n cross n matrices. This is m cross m matrices. And hopefully the cost function is such that these are positive. This is positive semi-definite and this is positive definite. So we'll talk about it in a bit. So I have at delta xt plus bt delta ut, and my cost function, let me call this c tilde delta xt delta ut equals to by the way, these all derivatives are evaluated at x bar t u bar t, as is the case here. So I've just suppressed those terms. So I have a linear system and I have a affine quadratic cost. So there is an affine term in x and u, and there is quadratic term in x and u. Okay. Now what I'm going to do is, I'm going to solve this problem as a function of delta xt. So instead of solving this problem as a function of xt and ut, I'm now going to solve this problem where I'm going to come up with a feedback policy for delta ut as a function of delta xt. So I'm looking for policy pi tilde of the form that takes as input delta xt. So I know my current state xt. I know where I was supposed to be, which was x bar t. So I can figure out what this delta xt looks like. This is my current state xt minus x bar t. And that will tell me what is the differential action that I need to take. And so the actual action applied is going to be u bar t plus delta ut star. Well, delta ut, just let me, star is when we do the optimization. Okay, so this is what my actual action is going to look like. And my actual action is a sum of open loop action plus a feedback action which takes into account deviation from the current state, deviation from the reference state. Okay. It turns out that, so in the assignment, what I have asked you to do is solve this optimization problem without this affine term. So I've removed this affine term from the equation. All we are doing is minimizing this quadratic cost, where you have x transpose qx and u transpose ru. I'm assuming that RT is positive definite and QT is positive semi-definite because that makes the math work beautifully. I have ignored these terms because these add additional complexity while solving the problem. You can totally solve the problem with those affine terms. It just adds the expression more cumbersome, so I don't ask you to solve that in your assignment. But if you ignore these two terms and you use this as your state dynamics and this as your cost function, you will see that you get a very simple recursion in your dynamic programming expression, and you get delta ut, which is a linear function of delta xt. I mean, delta ut star is a linear function of delta xt. And so in order to solve the problem in real world, all you have to do is store these matrices in your memory. Storing matrices is not a problem. Computing those matrices just requires matrix multiplication, matrix inversion, not a problem. Even if your M is 10 cross 10, you can totally do it. But if it was million cross million, then it becomes a problem, but we are not solving a million cross million problem. We are just sending a rocket to space, and so N is 10 and M is 5 or something like that. So it's in that particular vicinity. Okay. Now, what happens? What are these higher order terms? If we ignore these higher order terms, what exactly happens? You know, what we are really doing is model approximation, and then there is this theory which is extremely mathematically sophisticated. So therefore, I can't talk about it in this class. But what that says is, if you approximate the model with an approximate model and you solve for that approximate model, you get a solution which is approximately optimal for the original system. So I have the full model here and I have the full cost function. I came up with an approximate model here and I came up with an approximate cost function. And I solved this approximate cost function in order to compute the policy, optimal policy for this approximate problem. This optimal policy for the approximate problem is a near optimal policy for this particular problem. Okay. And remember, what we are trying to do is solve approximate dynamic programming. I don't want to solve dynamic programming exactly. I want to solve it approximately. I want to get a solution which is approximately optimal. So if it was optimal for me to send a rocket to moon and it takes 4,500 tons of fuel, I'm happy if I can reach moon in 4,700 tons. It's not going to change my life significantly as long as I can reach there. And certainly, I don't want to carry 6,000 tons of fuel because that would make my engineering far more complicated and sophisticated, and I don't want to go through that sophisticated engineering effort. Okay, so this is the way to solve this problem, this complicated problem, approximately. You did a model approximation, right? So this is the model approximation part. This is the cost approximation part. So you did model approximation, you did cost approximation. You can further do cost approximation by deleting these first order terms and just keep the second order terms here. And that will make your math extremely simple, very easy to compute, and you will see it in your assignment, how to solve this problem. Okay, and I'll do the final step problem so that way you know exactly how this problem is solved, and then you can repeat the steps at every point of time and get the Riccatti equation in your assignment. But any questions on this right now? Yes.
About the theorem you talked about, is there like a quantitative like metric? How approximate is it going to be?
Very good question. I think the answer to your question is there will be somewhere in some paper, somewhere that particular number will be there, but nobody cares about that number anymore now, because all of this is like, this is all old theory, 1950s, 60s theory. So I'm sure somebody in 1960s cared about it, but nobody cares about it now. Okay. If you have a humanoid robot, your UT could be 100 dimensional because you have every joint has a motor, and that motor has a state and an action. Maybe it has multiple states and an action. So so you can actually, so in robotic situation as well, you tend to apply this kind of algorithm because your microprocessor on robots is very small, and that microprocessor has to compute all of this actuation command. So you use algorithms of this type in order to figure out how to solve that problem in order to for a robot to be able to carry out certain exercise. And then there are multiple variants of these algorithms that have come up over the years. There is differential dynamic programming, there is ILQG, and then there is a lot of other algorithms that people have designed since then. So yeah, this is just the initial, like the algorithm number one, and then after this algorithm number one, there is a whole bunch of algorithms that people have designed in the past to solve problems of this type. But this is one of the simplest approximate dynamic programming algorithm that is there to solve problems. Any questions so far? Okay, yeah.
Oh, and also, is this a constraint optimization problem? Because
Right now we don't have any constraints. Like I said, there is no constraint here because the constraint versions are somewhat more complicated.
we said that the perturbation should be small.
Correct.
So should we constrain the outcome?
Absolutely. So the way to solve the constraint problem would be as follows. Okay, so I'll just give you a high level idea of how to solve a constraint problem, and I'll tell you also why constraint problems are difficult. So say you have a constraint gt of xt ut less than equal to 0. I can change it to gt of x bar t plus delta xt u bar t plus delta ut less than equal to 0. I can again do Taylor series expansion, gt of x bar t u bar t plus gradient xt gt of times delta xt plus gradient ut of gt of delta ut, and I'm going to ignore the higher order terms. Once again, whenever you have these inequality constraints, it appears because, let's say you have a battery pack, there is only so much current you can inject into the battery pack, otherwise it's going to blow up. But many a time those constraints are not absolute constraints, those are recommended constraints of some sort. So even if you are ignoring some higher order terms, it's not going to be too problematic. But if you want to be very conservative, let's say you are in a nuclear power plant and therefore you can't be like, you can't ignore these higher order terms, then you make it like minus epsilon or something. So that way you are being very conservative even after you are doing this approximation. So it depends on what your choice is. But let's say for now we make it 0. This is a constant term. This is a matrix times xt, and this is a matrix times ut. So now I have a constraint here, which is, let's say, A and B is used, C and D are R and C is used. Let's say I have a constraint dt plus et times xt plus ft times ut less than equal to 0. So I have this constraint that I have added. Sorry, I should use delta xt, delta ut less than equal to 0. So now I have these constraints added to this quadratic cost function. Now I need to solve this problem. Now I have to use QP. I have to use quadratic programming in order to solve this problem. I can't solve this problem by hand, and my solution will look far more complicated now. Okay, and remember, many of the times you are solving these problems on embedded microcontrollers, on devices, on robots, or on planes or flights or rockets. You don't want to add too many complications here. So the idea is that your this term is sufficiently negative that if you add these two constraints, it's always going to be maintained. So remember, this whole thing is less than equal to 0. If this is minus 100 and this is 10 and this is 10, then you will always be meeting that criteria. So even if you remove the constraint, you still get something which is bounded within the constraint. That's a hand wavy idea. Now, when you do the real world implementation, you get to realize whether it's satisfying those constraints or not. And the way to know whether it's satisfying the constraints or not is if the battery pack blows up, you will know that the battery pack has blown up. And you will know that this algorithm is not satisfying the constraint, and therefore you need to enforce that constraint and make sure that it is satisfied at every point of time. Okay. Any other question? Anybody has seen the Tesla when the rocket was supposed to come back and then it failed, it kind of blew up, right? So you've seen those videos as well. That's what happens when those constraints are somewhat ignored, or so you know that the failure has happened, right? So it's obvious that the failure has happened, and next time you will add further constraints so that that particular situation doesn't happen. So you remove those constraints thinking that they don't matter, and then the thing blows up. Then you realize that, okay, you need to put some additional constraints so that it doesn't blow up, and that's how the field progresses. So nothing against SpaceX as a company, but that's how the field progresses. You blow something up, then you realize, oh, I've forgotten a constraint, I need to put that constraint in there, and then you resolve the problem with that constraint, and then things work out. Or sometimes you may not have the complete description of the state space, right? So you assume that it has 10 states, but actually it had 15 states. So you've ignored those 5 states. Something blows up, then you realize, oh my God, those 5 states were very important. So I now need to build a sensor to be able to measure those 5 states, and now I'm going to make sure that I consider those as states of the system, and then I solve the problem. Okay. So by the way, this whole field of optimization and control, it's full of failures. Okay, so you don't succeed without failures, and sometimes people lose lives in those failures as well. So this is a very bloodthirsty theory that we are talking about. A lot of people have died trying to have died, after which the theory was able to be developed and got us to where we are today. Okay, so let's solve this problem at the final time step, because that makes things, I just want to show you how exactly to solve this problem, and then you can solve the rest of the problem at home in your homework. Okay, so I want to solve the following problem. My xt plus 1 equals to atxt plus btut. Notice that I'm changing the notation a little bit here, because now I'm changing delta xt to xt plus xt, and then delta ut, I'm changing it to ut. And then my cost function, c capital T plus 1 xt plus 1 is xt plus 1 transpose qt plus 1 xt plus 1, and then ct So at the terminal time step, my Vt plus 1 is equal to Ct plus 1. My Vt of xt is minimum ut in Rm Ct plus Vt plus 1 composition Ft. So this is minimum ut in Rm Ct of xt ut, sorry, Can I solve this problem? So I'm going to assume that QTs are positive definite, RTs are positive, sorry, QTs are positive semi-definite, RTs are positive definite. So I have something which is a convex function of U, and then I have another term of U here. So it looks like there are a whole bunch of things that I need to solve. Any questions so far? If not, I'll proceed. Okay, so I have, I'm going to collect the xt terms together. So I have xt transpose qt plus at transpose qt plus 1 at xt. Now I'll collect all the ut terms. So ut transpose rt plus and now there is going to be a cross term xt transpose at transpose and there will be a 2 here. I have 2 cross terms. I want you to stare at the equation and make sure that everything looks correct. I have collected xt transpose xt terms in one place, ut transpose ut terms in one place, xt transpose ut terms in one place. And I have 2 cross terms. One is because of this axt, this qt plus 1 getting multiplied to this. The second one is this particular term getting multiplied to this, multiplied to this. So there are 2 cross terms, and that's why I have this 2 factor here. And this is a scalar, so this transpose is the same as this because cost is a scalar quantity. So therefore, you can write it as 2 of this term. Okay, so now this is a positive definite matrix. This is a positive semi-definite matrix. I'm pre-multiplying it by a matrix, post-multiplying it by the same matrix. So this is a positive semi-definite matrix. Added to a positive definite matrix, this becomes a positive definite matrix. All eigenvalues are greater than 0. This is affine in U. This is quadratic in U. It's a convex function. How do I solve the minimum of a convex function? Take the first derivative, set it equal to 0. So I take the first derivative. First derivative is 2RT plus BT transpose QT plus 1 BT.
The expression 2A plus BTO, the power of T, is not a derivative. It's a matrix expression
I'm not
involving
asking
addition
you.
and
Gemini thinks that they are also part of this class. Two BT transpose QT plus 1 AT this is at UT star. So this implies that UT star equals to minus RT plus BT transpose QT plus 1. This is my pi star T. Sorry? LQR. Okay, so I solve this problem. I get ut star as a function of xt. I remember that the argmin is pi t star. So I've set the argmin as pi t star of xt. It's a function of xt. I have a whole bunch of matrices getting multiplied, inverted, and multiplied again. Multiplication of matrices, easy operation. Inversion of small matrices, easy operation. So this whole thing is easy. There's no difficulty in doing this. I can in fact compute this thing offline. Like I'm sending a rocket to space, but I can compute it on the ground, and then I'm going to store it on the rocket that's going to the space. So I can do that, and that'll help me with the memory. Now, if I had a constraint here, which is dt plus some function of xt plus some function of ut less than equal to 0, now it becomes very complicated. Now I can't solve it like this. I can't solve it by hand. I have to actually use a computer and a QP solver in order to solve that problem, and that's very complicated. Okay. The other thing is, now I need to substitute this ut star in this expression. Okay, so I have to substitute this expression for ut star here, and I have to substitute that expression here. And what I would see is my Vt of xt becomes xt transpose some matrix. People generally call it Pt time xt. Okay, that Pt is going to be a very complicated matrix involving some of these terms. And what you will see is that Pt has some update term. So it will look something like At transpose. I'm going to define Pt plus 1 equals to Qt plus 1, and then Pt equals to At transpose Pt plus 1 At plus Qt plus minus At transpose Qt plus 1 Vt inverse this inverse is the same as this particular matrix. And this is known as a Riccatti equation. So by substituting the expression for ut star in the cost function, you get the value function at time xt, because value function is the minimum value of this function. So by substituting ut star, you get the minimum value. You will realize that the minimum value is of a quadratic form, and the quadratic form can be updated in this particular fashion. So now what you have to do is, all you have to figure out these matrices At, Bt, Qt, Rt, Qt plus 1, and then you can keep computing these matrices. These are all matrix multiplication, and you get the value function, and you get the strategy, the policy as a function of state. You get that very easily through matrix multiplication. And that's the benefit of this LQR approach. So somebody has given you the trajectory, you do Taylor series expansion around that trajectory, and if you have constraints, you kind of ignore those constraints. You get everything which is very clean, very nice, very easy to compute, no complications, and then you can start executing it on using the onboard computer that you have. Okay. Naturally, the next frontier involves adding those constraints back in. Nowadays, if you think about robotics, the constraints are somewhat more complicated. So a rocket is going into the space. It's not going to see anything in the space. Okay, it's pretty much clutter free. However, if a robot is supposed to walk around in this room and maybe do the vacuum, now it has to go through all this cluttered space. And at every point of time, somebody will come push the chairs here and there. And so the space looks completely different tomorrow in comparison to today. So now all of those constraints gets added back in. but then you also have much more powerful microcontrollers on the robots to be able to compute the optimal solutions and to be able to execute those optimal solutions. So this is classical stuff. This is the stuff from 1960s and 70s that has brought to us where we are today. This may not be the good stuff moving forward, but it still helps you get somewhere, after which you have to add a lot more complications in order to solve the problem. So today, I think we are done with today's lecture. I did not tell you about singular perturbation theory. So the next class, I'm going to talk about singular perturbation theory, and I'm going to talk about differential dynamic programming. So that's another topic that I want to cover for approximate dynamic programming. And and those are the two topics that I'll cover on model approximation and cost approximation. After which we'll talk about value function and policy approximation. So that topic will consume like 2-3 lectures. One thing that I still want you to think about moving forward. So it seems to me that before Thanksgiving, the entire syllabus will be completed. And the reason why syllabus is getting completed so early is because you guys don't ask questions. Okay. However, what I'm trying to think about is post Thanksgiving, we still have 5 lectures. I'm not sure what topics I should cover. So if there is some specific topic of interest you want me to cover in the class, I'll definitely cover that. If you don't want me to cover anything, like you don't even have questions there, then I guess we can all have our 5 hours back, and then I'll just cancel the classes in December. And you can focus on your project. And if you have any questions, feel free to reach out to me and talk to me. So the homework for you, aside from assignment 6, is to think about what topics you would like me to cover from 1st December until 10th December. If there are no topics, we'll cancel the class. If there are topics, I'll try to cover those topics in the class. Thank you.